Welcome to Simerics. The following presentation demonstrates the direct integration between the turbo machinery design software, CFturbo, and the multiphysics virtual testing computational fluid dynamics software, SimericsMP. A nearly complete design of a blower was created in CFturbo, and the design process is shown in a related video. Here we will start with this blower made in CFturbo, perform the latest operation needed to complete the model, and then export it into SimericsMP. The design process is iterative and begins with the creation of a blower in CFturbo, which is then exported into SimericsMP, where a CFD simulation is performed and evaluated to determine how to further modify the blower in CFturbo in the next design iteration. This continues until the blower is optimized. Here are some screenshots of some of the panels in CFturbo. The design process begins by specifying the basic performance requirements such as flow rate, head, RPM, fluid type, and efficiencies. So here we are in CFturbo, and this is the blower model, which is almost finished. This is the global setup panel where we input the flow rate, head, etc. Based on empirical correlations from experimental data, CFturbo calculates the main device dimensions, and the user proceeds through the design procedure to arrive at the final design. At this point, the last thing left to do before exporting is the model finishing of the impeller. You can see the state of the model in the message panel on the right, and in this case you see that model finishing has not been done for the impeller. So we go to the impeller panel, choose model finishing, put it on solid trimming, and hit OK. Now we're ready to export. So go back to the project panel, choose export, and under the interfaces, under CFD, we see that it's set to export to SimericsMP. We could also just as easily export to pump links. It works the same. Next we go to components. We choose the components that we want to export. That would be the impeller and the volute. Export destination. We give it a path to tell it where to dump the files, give it a file name, and at this point we can export just the STL CAD surfaces. We'd go down here and hit this export data, or if you want to export it into SimericsMP where it will automatically mesh it and set up the CFD model, then activate the open exported files. Now we will export it. I'll skip past the loading process and go directly to SimericsMP. Here's the blower in SimericsMP. Now it's meshed, the volumes are connected, the boundary conditions and volume conditions should be correct corresponding to what was specified in CFturbo, and the rotating volumes are put into a non-inertial reference frame. So let's go through and check. First we see that this is a steady state run. It could also have been a transient run, but for now we'll run steady state. Since the impeller volume and its surfaces are rotating, we need to specify it in a non-inertial reference frame. And we can see that CFturbo did activate this. And we see that it's rotating clockwise at 4,000 RPM about the Z-axis. Similarly, the blades, hub, and shroud are also rotating, and they have the same specifications as the non-inertial frame. If you change one of these quantities like RPM in the rotating walls, don't forget to change them in the non-inertial frame. It will not automatically change it. The rotating walls serve to add momentum sources to the momentum equation so that shear forces are accounted for. We see that the output for the rotating walls is torque. I'm going to add power as well. Let's look at the impeller inlet and see whether it's set up. And yes, it is. It's a total pressure boundary at 1 atmosphere. And the output here is mass flow rate, mass average total pressure, and average static pressure. And the rotor outlet, although it says it's a wall, it's actually a fluid-fluid interface since it's been connected to the volute volume through an MGI. MGI stands for Matched Grid Interface, which allows the rotor outlet face to slide by the volute entrance face while still communicating numerically to one another. Let's check the volute outlet, and we see that it's volumetric flux boundary condition as we input that in CFturbo. Now we're ready to launch the solver, analyze the results, and make informed design change decisions for the next design iteration. I'll skip ahead to the results to show you the typical output. So we see that we have a converged solution now, and you can see we've plotted the torque, on the rotor, the power on the rotor, and the mass flux in and out of the blower. So in conclusion, to summarize, we exported a blower created in CFturbo into SimericsMP and saw that the mesh was automatically created, the boundary and volume conditions were set up, the volumes were connected, and the rotating reference frame for the rotating parts was activated. Please feel free to contact us if you have any questions or if you are interested in related presentations. If you would like a demo of Simerics or pump links using your device, let us know and we will make the necessary arrangements.